Now we consider systems described by finite order differential equation, linear differential equation, which means that you have some linear combinations and some differentiators. In this example, we consider that y of t n means just derivative d2 dt of y of t, but not one times but n times. That means that you apply d2 dt n times on y of t, and then you multiply this guy by an, and then you apply n minus 1 times, you apply it by an minus 1, and so on, and then this linear combination is equal to x of t. Obviously, we could have had this plus d2 dt of x of t multiplied by another constant and so on, but that is not very hard to analyze, because we could first give x of t to a differentiator d over dt, then give it to another differentiator d over dt, etc., and then multiply by this by a constant, multiplied, and then add these guys together, and then get one output, and then apply this output to this system. So, and then we do it combination of cascade of two systems, and then we already have learned how to deal with this guy in previous examples. So in this example, because this is a linear system, I apply only mean of x of t here, mu x of t, and I get mean of y of t. Okay, so if I apply this one, so I will have the same differential equation. So by solving the same linear differential equation, finite order linear differential equation, at the input I put the mean of the input, at the solution of this differential equation, it becomes the mean of the output. Now, so for this system, if I want to use using this system, if I want to calculate r, x, y of t1 and t2, I could consider this differential equation and multiply both sides by x of t1. So I will get x of t times x of t1 is equal to a naught y of t times x of t1, and then plus everything else plus an, and then d to dt n times of y of t times x of t1. Now I could apply expectation operator on both sides of equation. So expected value of this guy becomes rxx of t1 and t, and expected value of these becomes rxy of t1 and t, a naught, and so on, and these will become an d to dt of r x y of t1 and t. So we see that this is the same linear differential equation that was here, but the input is this one and the output is this one. So what I could conclude is that I could solve the same linear differential equation for this input, and the answer, the solution of the differential equation, becomes the cross correlation between input and output, and that's interesting. So the cross correlation between input and output is a solution of this differential equation, the same differential equation we had. But remember that here I keep t1 is fixed, is a fixed number. I solved it for the differential equation, I solved it for t. So, and the output is the response of the system to this autocorrelation function. So the input autocorrelation function, the response gives you this one. And this is the block diagram of what we said. Similarly, you could fix t and then apply same differential equation to this input and get the autocorrelation of the output. So you could solve it as you see here.